I would like to welcome you to today's webinar. We will discuss today mastering power measurement key specs to get it right. You can see this webinar as practically as a checklist on how to select or what are the most important criteria for the selection of a power measurement instrument. Before we continue with the webinar itself, I would like to introduce myself first and then introduce also my colleagues who will be joining this webinar today. My name is Velizara. I am the product manager for the data acquisition devices, and I will be today your moderator, and I will also present part of the webinar. And my colleagues who are experts in power measurement have also joined today. So I'm happy to welcome Roy and Nishi. Roy.
Okay. My name is Roy Hali. I'm Senior Application Engineer at HIOKI Europe. I work at HIOKI Europe since 2020, and I have already more than 25 years experience in test and measurements. And what already mentioned by Velizara, my specialty is power measurement.
Thank you.
So my name is Ryuji Nishizawa. I have been working with HIOKI Corporation since 2012, and last year I'm transferred to here in Germany. So now I'm working in the HIOKI Europe as a product manager, and I'm mainly in charge of the power measurement. So it's nice to meet you today.
Thank you very much, guys. Before we continue with the webinar itself, there are a few rules that I would like to explain. The webinar will take about 30 to 40 minutes. We will have time for questions afterwards. Of course, you can also ask your questions during the webinar. You cannot do so vocally because you will be muted. But you can use the Q&A function in different languages. You may see F and E, or depending what is the wording in your language. Please do not try to use the chat function because it is disabled. We will record this webinar, so in case your colleagues missed it or you liked it so much you want to see it a second time, please feel free to check out the recording afterwards. And now we're ready to start with the webinar itself, and I would like to give the word to Roy.
Thank you, Velizara. Well, let's start with some background information. The decarbonization of modern society in many situations will lead to energy and electricity conversion. This slide shows you the examples that are available, like, for instance, wind and solar power generation, electrification of transport, and climate control systems. To avoid energy waste, it is key that the conversion is done as efficiently as possible. To ensure this, it is necessary to use measurement equipment that fits the needs and gives you reliable and accurate measurement results with an excellent repeatability. In today's webinar, we will focus on solutions for research and development, production and field testing of power electronics, and talk about the most relevant considerations that help you to select the power measurement solutions that fit your need best. So, what are the main considerations? Well, let's start with measurement items. Are you just interested in total power? Or do you want to measure a wide range of parameters, including, for instance, harmonic distortion up to the 500th order? Or do you want to combine power measurement with temperature measurement? The next one will be the number of channels, synchronization, and multiple devices. Depending on the needs, there are solutions available from single channel up to 120 channels. Velizara will go into this subject later on. Then there is sampling rate, data update interval, and frequency band. Also, depending on your applications, for instance, when you're measuring the output of an inverter with a pulse width modulated signal, then sampling rate and frequency band are very important. But in another situation where, for instance, you're measuring the efficiency of an EV, you're measuring normally only DC, and then these parameters are less relevant. Maximum input voltage and current. Standby power of consumer electronics is in the range of milliwatts, whereas a power generator of a cruise ship is in a megawatts. It is clear that you need different solutions for each application. Power accuracy. What level of accuracy do you need? Ryuji will explain how to calculate power accuracy of your measurement system, helping you to consider what accuracy you need. And the last one that we also will address is data output. How to export your measurement data. We will show you the options. Depending on your needs, you can select the best one for you. Now I would like to hand over to Ryuji.
Thank you, Roy, for your introduction part. So from here, I'd like to explain about the key specs, which we should know before choosing the power measurement instrument. So first topics is a very general topics. So before choosing the power measurement instrument, it is important to first ask, what exactly do I need to measure? So is it just the basics? So voltage and the current and the power is already enough? Or do I also need to evaluate efficiency and harmonics? And if I'm measuring a motor, do I want to include torque and speed as well? So standard power instrument can handle voltage, current, power, and efficiency and harmonics. But if you need a more advanced measurements like torque or speed, you will need a more advanced power analyzers. So clearly defining your measurement needs will help you choose the right instrument. So second topic is also the general one. So when thinking about the channels, how much channel do you need? Let's think about if we want to measure the inverter. The input side is the DC, the output side is the three-phase AC. In that cases, you need 4 power channels. But how about if you need the 3 inverters simultaneously? In that cases, you need 12 channels. So standard power analyzers offers from 1 to 8 channels. But what happens if I need more channels, like a 12 channels measurement? So mainly there is 2 options to solve this problem. First is using the modular data logger. With the right configurations, this allows you to measure up to 12 power channels in one system. So second one is synchronizing the multiple device power measurement instruments. So the table below is a summary of the synchronizations. There are 2 types of the synchronizations: the electrical method by connecting the BMC, and the optical method by connecting both devices by optical cable. And both types using the primary and secondary settings to align a data update interval. But by using the optical synchronizations offers some clear advantages. You can change the settings of the secondary device from the primary device, and it supports long distance connections. Up to 500 meters, it can be possible to connect it. And that makes it ideal for your device are located in a separate room. So from here, I like to explain about the specs, which you should know. There is mainly 3 important specs: the sampling rate, and the data update interval, and the frequency band. I will clarify about that word's meanings, and I will explain about the differences, those terms. So first, let's start with the sampling rate. Look at the diagram here. The yellow line is the original analog signal, and the blue dot shows where the device takes samples point. The sampling rate means how many of those sampling points are captured per second. So, for example, a rate of 100 kilosamplings per second means the device samples 100,000 points every second. And next one is the data update interval and how it is different from the sampling rate. Just like before, the yellow line shows the analog signal, and the blue dots are the sampling points. So what happens if we change the update interval from 15 milliseconds to the 10 milliseconds? The red dot shows the data points that are actually saved and indicated on the instrument. So even though the device samples continuously at each blue dot, the value you can see on the display or as saved data, like voltage or power, as calculated over certain time windows. This certain time window means a data update interval. So with a 15 millisecond interval, you only get one data point every 15 milliseconds. But with a 10 millisecond up interval, you can get 5 values over the same time span. So if you want to track a signal changes more closely, it's better to use a shorter update interval. So now let's talk about the frequency band. And this simply means the range of the frequency that a power measurement instrument can effectively measure. Take a look at the two pictures. On the left, we see a grid power measurement. This means like checking the power consumption of the factory equipment. Here, a frequency band of up to few kilohertz is usually enough. But on the right, we have an inverter using the power semiconductor like 𝗪𝗪𝗀 or GaN. In this case, the frequency band of up to a few megahertz is required. The key point here is the required frequency band is determined by the maximum frequency of the signal to be measured. In other words, it's really depending on the applications. So, and here's an important about the frequency band and sampling rate. Take a look at this diagram. The yellow line shows the actual analog signal, and this is 4 Hz. And the blue dots are the sample points, and the blue line shows how the instrument thinks the waves looks like based on those sampling points. As you can see, it incorrectly interprets 4 Hz signal as 1 Hz signal. This happens when the sampling rate is too low, and it is called aliasing. We won't go into theory here, but the simple rule is this. To measure signal accurately, the sampling rate must be at least twice the highest frequency in your signal. Then let's look at a summary of these 3 key specs points. So the first one is a grid power measurement, like checking the, as I discussed earlier, the checking the power consumption of factory equipment. So here we are typically dealing with the 50 Hz signal and its harmonics. The reason we need to include the harmonics is because of the distortion from the other equipment they have. So it is common to measure to the 40th harmonics. So which means the frequency band of at least 2 kHz. So because 50 Hz signal is multiplied by the 40, it means 2000. So 2 kHz frequency band is required for this measurement. Regarding to the sampling rate, as we discussed around earlier, to avoid the aliasing, the sampling rate must be at least 4 kilos samplings per second or higher. And regarding to the data update interval, since we are focused on the overall power consumption, usually the 1 second update interval is enough. So now compared to the switching inverters, especially using the 𝗪𝗪𝗀 or GaN power semiconductors. So in this case, you need to measure not just the fundamental signal and its harmonics, but also the switching frequencies and its harmonics. So if switching frequency is at 100 kHz, you may need to capture up to the 10th harmonics. because up to the 10th harmonics, we can see some of the power consumption. At least the frequency band will become a 1 megahertz of the frequency. And to avoid the aliasings, the sampling rate has to be 2 megasamplings per second or higher. And because compared to the grid power measurement, switching inverters power changing very rapidly, so it is better to have a more faster updating level. And 200 milliseconds or faster is better. So as you can see, the required specs depend heavily on the applications. So from here, let's talk about the very key element for the power measurement, voltage and current. So especially first, I like to talk about the max input voltages. If the voltage is under 1000 volt, it is simple. Many of the power measurement instruments can handle it directly with no extra components or added error. It can be measured. The problem is if it exceeds 1000 voltages, there is mainly three options here. So first one is using a differential probe. So it sounds very convenient, but in reality, it's not ideal. That is because accuracy is poor and the frequency characteristics are unclear. So we generally don't recommend this, especially for power measurement. And second one is using the measurement transformer. So this works for basic power frequencies like 50 Hz or 60 Hz. But if your application needs a wider frequency band, it's not a good fit. And the third one is using the voltage divider. So this is the best option. It supports a wide frequency band and introduces only minimal error. Our voltage divider supports up to the 5000 voltage measurement. So that's why we recommend using a voltage divider for high voltage power applications. So second one is important key element for the power measurement is a current. So for here, I mainly am talking about the way of the sensings for the current. There is mainly two sensing methods. Direct current sensings and external current sensings we have. So on the left, we have the direct input method, usually used when the current is below 50 amps. And here, the current flows directly through the instrument. So to measure this way, you need to break the circuit and insert the instrument. So since there is no extra sensors, accuracy is very simple. Total accuracy equal instrument accuracy. On the right, we see external current sensings, which is common for larger current but also it is possible to measure low current from 2 ampere to the 2000 amperes. So our external sensors detect the current and pass the signal to the analyzers. In these cases, the total accuracy equal instrument accuracy plus sensor accuracy. So to wrap up our section on the voltage and the current, let's compare power accuracy of two current measurement methods. This table shows the example for the DC power measurement. So by the way, and the little number is actually picked up our actual power measurement devices. So on the left, we have a direct input. As mentioned earlier, the total accuracy here equals to the instrument accuracy, so that will become 0.2%. And on the right, we see external current sensings. In these cases, total accuracy includes both instruments and the sensors. It will become 0.12 plus 0.032. In this case, total accuracy will become 0.152. So surprisingly, and this method is actually more accurate than direct current sensings. So this is possible because HIOKI develops both high precision sensors and the power analyzers together. So, but however, not all sensor setups will outperform direct input. Accuracy still depends on sensors. So Velizara will talk more about this current sensors type later. So aside from accuracy, external current sensors also offer some practical benefits. The flexibility across a wide current rating we can offer from a 2 ampere rating current sensor to the 2000 current. And the stability since there's no self-heating. And the easy installations. Or by using the clamp sensors without disconnecting the wires, you can measure the current. So finally, I'd like to quick look at the data output, which plays a key role in analyzing result and integrating with other systems. On the left, you can see the common output interfaces like RS232C, LAN, USB, ZPIB, DA output, and CAN, which is especially popular in automotive world. And on the right, we have the different output formats. This includes binary files for compressed data and CSV file for Excel analysis, and CAN or CAN-FD for automotive communications, and analog output like plus minus 5 volt or synchronizing with other instruments. So choosing the right combinations of interfaces and format makes post-processing and the system integration much smoother and more efficient. So if you have a question from my part, please send in the question to the Q&A boxes. Then I'd like to take over the voice to Velizara.
Thank you, Ryuji. Now I would like to go a bit more concrete and give you a few examples with our power measurement instrument so you get a better feeling how the specifications differ from device to device. We will skip talking about the maintenance part, so we'll not talk about power quality analyzers and power loggers for energy consumptions. We will focus today on a comparison between 4 different devices. We will take one of our power meters, the PW3337, 2 of our power analyzers, the PW8001, which is our flagship power analyzer, and the PW3390 as a WLTP standard, which Roy will explain in the end of this presentation. And the reason why I'm here today is also we have a modular data logger, which is capable of measuring also power. That's the LR8102 data logger with the power module M7103. Now I will go step by step, the way Ryuji explained the different specifications and compare the different devices. Looking at the basic specifications or the basic measurement items of these different devices, you can see that they can all measure standard components like voltage, current, and power. And they can also all measure efficiency, for example. And looking at harmonics, this is the first difference you can see, that most instruments can measure up to the 50th harmonic, except the PW8001, which goes up to the 500th harmonic. The second big difference is, of course, the motor parameters. You can only measure motor parameters by using a power analyzer, so this is not possible with a power logger or a power meter. Then we discussed about the channels and how many channels you need. You have to put some thought about that before buying the device, because some devices are limited. Looking at the power meters, they go from 1 to 3 channels. In that case, it's 3 channel. And we have also data loggers, which offer up to 12 power channels of simultaneous measurement. And then the power analyzers with 4 and 8 channels. But these devices are also differing in the sense of how many can you synchronize and how you can synchronize. As already explained by Ryuji, you can synchronize devices either electrically via BNC or via optical cable. And here you can see also some differences between the number of devices that you can synchronize and, of course, the number of channels that you can get out of the whole combination. And here you can see that with the data logger, for example, you can synchronize up to 10 data loggers with 4 modules each, giving you 120 power channels. whereas the power analyzer 𝗪𝗺𝗀𝗃 has less channels, but it offers you more measurement capabilities as general. One topic that we have not mentioned or haven't spoken about yet much is the AC-DC synchronization source sharing. This is only relevant if you're looking into measuring, for example, efficiency, so AC and DC signal, and you want to synchronize these. You can see that most devices have this capability of synchronizing these signals. However, it is only possible mostly within one device. Except for the data logger LR8102. This one can also synchronize in between different devices. We also discussed shortly about the sampling rate, the data update interval, and the frequency band, and how these are related to each other. And here you can see a very nice table that explains how these different devices compare in these three specification points. And you can see that we have very different sampling rates with the power analyzer as the most mighty tool, let's say, with the fastest sampling rate of up to 15 megasamples per second, and also the fastest update rate. We have also different frequency bands. Then again, looking into the application, are you looking into lower frequencies? Then maybe a power meter is more than enough with 100 kilohertz, or a data logger in that sense. Or are you looking into higher frequencies analysis with a 𝗪𝗺𝗀𝗃 of up to 5 megahertz. As Ryuji already mentioned, we also have different, he explained the different, voltage. The direct input voltage could be below 1000 volt. We also have devices that can handle more than 1000 volt. But you always have to keep in mind there are two specifications. One is the maximum input voltage. This is practically the voltage that you can directly input or give the device on every single channel without having any issues. And the second is the isolation to earth. And here you have to also take care if the device is category 2, which is low voltage usage, so where you are going to use the device, and category 3 would be, for example, distribution boards and so on. So this is something that you just, it's just a table that you have for later reference, but this is something also you have to be careful about in order to have a safety power measurement. The devices, as already mentioned, have different power accuracy. Here you have a very nice diagram comparing the active power accuracy to the frequency band. And here you can see, for example, the PW3337 has a power accuracy, which is the instrument, and the total accuracy, because this instrument measures power directly, current is measured directly. So the total accuracy would be 0.15%. The other instruments that you can see in this diagram all use external sensors to measure the current. So the accuracy that you can see in this table is only the instrument accuracy, and to this accuracy you have to add the accuracy of the current sensor that you would like to use. And here we have very big differences. It depends what is your application. It depends how high accuracy you're aiming for, and of course, what frequency band and what current you want to measure. We have different solutions, different external sensors. So we have the pass-through current sensors, which offer the highest accuracy and the widest frequency band up to 10 megahertz. And of course, the highest current with up to 2000 ampere. Nevertheless, these are not as easy to wire as, for example, a clamp-on sensor, obviously. So they're usually used in not finished products or on test benches. Then we have the clamp sensors. Here you can see two examples for clamp sensors. One, I think, is well known in the market, is the 𝗪𝗂𝘂𝗪𝗺 series, which offers a fairly good accuracy and a very wide bandwidth, up to 1000 ampere. And it is typically used for finished products because you can simply clamp it to the DUT that you would like to measure the current from. the newest current sensors that we just launched a few months ago, the 𝘺𝗂𝗂𝗋 and 𝗃4, are capable of measuring 200 and 500 ampere, and they have very high accuracy as well, but a more limited bandwidth. These are excellent to install because they are extremely small, so you can use them in very tight spaces where you don't have any space at all. So these are different options, and as Ryuji already explained, the total power accuracy in the end will depend on the combination that you will select, either a direct measurement of current or using an external current sensor, and depending on which sensor you use, that will also influence the accuracy in the end. Last but not least, I would like to show you just a quick comparison between the data output. We already spoke about their different output interfaces. The good news is that most devices have either an RS-232 interface or a LAN interface. So you have very standard options to export data. Some of the devices also offer, which could be interesting for the automotive, offer CAN output, like the data logger and the PW. There you can export the data via CAN. And there are also different output formats that you can use. Also good news, all devices offer the text format, and there are also some other types of format, which may include also more important information. So you always have to think, how do you want to export the data and how do you want to analyze the data later on? Now I finish with this part. I will hand over to Roy, but before I do so, again, I welcome you to ask questions, and Roy will now wrap up.
Okay, well, we are going to look at applications, and we have made this kind of table to give you some insight about applications and where our instruments fit better. In this slide, we are looking at research and development applications. And for instance, if you look at renewable energy, then you can see that the LR8102 in combination with the M7103 power measurement module is very much suited for this application. The reasons for that are mainly that we can measure the highest string voltage of 1500 volt directly with the module, and it's also possible to measure up to 120 channels. And we also have the capability of the AC-DC synchronization, meaning that we can synchronize at the input when we have many input channels from solar strings. We have DC signals on that side. We can synchronize all these channels with the AC signal that we have on the output. Another application for research and development, which is interesting, is the WLTP standard. As you can see, the PW3390 is also very suited for that. And the reason for that is that it's basically the standard of measuring WLTP. And the reason is that we have the combination of the power analyzer with our own current sensors in the CT6830 and CT6840 clamp-on sensors, and the combination of these two are within the specifications, the WLTP accuracy specifications, and therefore they're very popular for that application. And then we're going to the applications in the manufacturing and field testing, and we have the same way of looking at these kind of applications, and the ones that I would like to highlight are the PW3337 for production testing of household appliances, and these are very well known in this kind of applications because it's very easy to integrate these compact equipment, and also they have very basic control configurations. And that makes it easy to integrate them. The next one is again the LR8102 in combination with the M7103 for product testing of household appliances. And the reason why that one is so interesting is that it can measure up to 120 channels simultaneously. So if you have multiple production lines, then you can do the tests simultaneously and get the results in one time. Okay, and then another application which is worth mentioning is the PW8001 for onboard chargers and efficiency testing. And this one is particularly interesting for that application because in that situation you will need you have the high switching semiconductors integrated in the circuitry, and they create noise, and therefore you need to have a very good noise resistivity, but you also need the high accuracy to be able to measure the efficiency of this kind of devices. And also important, you want to have a very good reproducibility of the measurement so that you can compare different measurement results on the production line. Good. Then, let's start with a wrap-up. I would like to ask you once again, this is the last opportunity. If you have any questions, please put them in the Q&A box so that we can take them and answer them later on. But first, let's wrap up this seminar. And you can see that we have addressed the following items, measurement items. So we have seen that there can be a wide variety of measurement items, power, harmonics, temperature, and we have also looked at the number of channels, and there is also a lot of flexibility in that field. Ryuji has given a very clear explanation about sampling rate, data interval, and frequency bandwidth. And then we have seen the maximum input voltage and what we can do if we exceed the maximum input voltage of the measurement device. We have looked at the power accuracy and have shown you how to calculate the power accuracy of the different applications. And then in the end, we have looked at the data output, of course. We have also much information available on our website, so you can visit our website for further information. But of course, it's also very nice to contact us and to send you the questions, starting with the Q&A box at this moment. All right. Then,
Okay.
Velizara.
It's time for the questions. We have received a few questions. You are welcome to still ask questions. We still have some time. I will put this in the end so you can see we have also a website for power measurement where you can see an overview of the power measurement solutions that we have. But now we go to the questions. The first question was, if we have an analog signal of 1 kilohertz, what could be the maximum recording time?
The maximum recording time.
At 1 kilohertz. So that would be 1 kilohertz update interval.
So how should I say? The recording time is determined by the data update interval. So, and as we talked before, the sampling rate is it's already fixed one. So if the how should I say, instrument have a 1 mega sampling per second, always that instrument working over 1 mega sampling per second. But you can change the data update interval, for example, 15 milliseconds or 10 milliseconds. So it depends on the what data update interval you would like to set and how many parameters you want to measure. And you can save the data onto the USB. In that case, is that also depending on the, how should I say, the capacity of the storages. So, yeah.
So this means it depends practically on how many channels you're measuring, how many parameters you're measuring. And also, of course, we have been given here 3 different update intervals. Obviously, the slower the update interval, the more you can record. And also, it depends on which format you select, I suppose.
Yeah, exactly. So binary format is a compressed data. Yeah, correct.
Yes, perfect. All right, and it depends on the storage that you're using. As you already mentioned, you can save the data on a USB stick, so it depends. The USB sticks we offer are 16 gigabyte, but you have freedom, of course, to use also other storage devices.
Yeah.
All right, the second question, what is the voltage insulation max value between channels in the 𝗪𝗺𝗀𝗪𝗀 So what is the isolation between channels for the 𝗪7001 and 𝗪7005?
Yeah.
Yeah.
The
For the 𝗪7005, that is 1000 volt, and for the 𝗪7001, which is the high voltage input unit, that's 1500 volts.
I think this was also given in the table that I presented. So we will, of course, share all the materials. So you will have that information also available later on as reference. All right, we are using a PW3390-03 and a CT6843 current clamps in Germany. For technical support, who can we contact? This is already on the screen.
screen.
So if you have any technical questions, always feel free to directly address PM support. One of our power colleagues will take over the inquiry then.
Yeah.
All right, and we have two questions. You mentioned the frequency range and sample speed depends on the maximum frequency of the input signal. How do you need to determine the frequency range and sample speed for a PWM signal, as these have a lot of higher frequency components?
Yeah, thank you for very good questions. So, so it depends on the, how should I say, for thinking about the power measurement of the switching frequencies, it is theoretically the PWM signal is, how should I say, that is a square waves, and the current switching frequency will become a triangle wave. So it is a deep, but theoretically it is calculated. Switching frequency first orders power. And when it comes to the tens, it will become almost 1,000 times smaller. So we think it is better to catch up to the tenth harmonics of the switching frequencies. So, but I think this is a very technically difficult. So I think I will send you an email later.
Okay, perfect. Thank you. And the same person has a question also. How does update interval influence measurement accuracy and repeatability?
Well, in our situation, we don't have any deterioration of the power accuracy when we reduce the data update rate. So even at 1 millisecond, we can guarantee the specifications, the accuracy specifications of the power measurement with the PW8001.
All right. We have a comment from one of our colleagues who said that we should mention, we apologize, we forgot to mention that, of course, we have also drivers for the instrument. So there are, for most instruments, we have a LabVIEW driver, and you can also use skip commands to operate the instruments. This is just a comment, no question on this. The next question, does the same philosophy related to the onboard charger related to the power analyzer selection applies to off-board DC fast chargers, even if we are not developer of the power modules, but we look at the unit, its complete system for overall evaluation?
Yeah, for overall evaluation of chargers, it depends on what kind of signals that you want to measure. If you have a fast charger which is connected to the grid and has a DC output, then it's not essential that you have a very high bandwidth. But if you are in the development stage of that same charger, then probably you want to identify where your losses are. And then you are going to look at the high frequency switching semiconductors inside. And then you want to figure out where your losses are. And in that situation, it will be important to have a wide bandwidth and a high sampling rate to have accurate measurement. So determining where you have your losses, if you want to measure, for instance, the component losses, the losses in a inductor inside your system, then you need the high frequency bandwidth.
Mm-hmm. Thank you. A question, can you synchronize PW6001, I suppose was the question, and PW8001? It's an interesting question.
Sorry, does it mean synchronize with the PW6001 and 8001 by optical link?
Yes.
Unfortunately, it's not possible. Only the same instrument can synchronize by optical.
Mm-hmm.
Yeah, also, but that's the same goes for the BNC nut. It's not possible to synchronize a PW8000 with a PW6001. Yeah.
There was a question if we have comprehensive videos which explain how the power instruments are set up, how to connect, how to measure, how to monitor, how to log the data. I don't think we have these videos.
Not yet.
Not yet, but yes, but I was actually discussing that with some colleagues, and that's actually a great idea and a very good question. We will think about making such videos because, no one reads the instruction manual, unfortunately, nowadays. All right. The higher accuracy with external current sensors compared to direct current sensing is true only for HIOKI's power measurement solutions, given that HIOKI manufactures their own current sensors, or applies for other power analyzers in the market?
I would like to answer that question. It is a very big advantage that we have our own current sensors, because the current sensors that we use, they are designed for power measurement. So from the beginning on, we are looking how to get as much accurate results for power measurements. Our competitors, they have third brand current sensors, and these current sensors are not designed purely for power measurement. And because we have the combination of power analyzer and current sensors, we have an optimized solution. And also the current sensors and the power analyzer, they can communicate with each other, and therefore solve issues like time delay of the current sensors and compensate for that. And that's a very big advantage, especially when you are going to measure high current and high frequency applications, like, for instance, an inverter measurement, or, for instance, the loss of a inductor or a reactor.
Okay, thank you, Roy. Where we have another question. One of our customers is using the PW3390 and is sampling at 200 kHz. And he's using a CF card to store the data. So the question is, how can you extend this, because the logging period is very short, how can we extend that period? Are there other options that we can log data for longer time periods with the PW3390? I am coming up with one that would be.
I think that will be a question that we will answer in writing, because it's a little bit detailed. Okay. We don't all have the data in our heads, I think.
All right. Yeah. Okay, then we will check and we will come back for email on this question. Yeah. If there are 10 machines on one floor and we want to measure the power, we need to install and connect to a modular at a power distribution panel. from where the power is distributed to the machines. So if you use the modular power analyzer.
The logger, probably.
The logger is.
Yes. Well, what I would recommend is to have the logger close to the application and then use an optical link to connect them. I think that would be a good solution, not Velizara?
Yeah. That's the best solution, obviously, because if you want to measure power, you will also need to use the external current sensors in that case.
Yeah. If, however, the two of the applications you mentioned, there are 10 in one room. So if there are two very near to each other, then you can combine them in one power logger. Of course, that's a possibility.
I'm not 100% sure that I understand the question correctly. If it refers to how to power the logger itself, you can use also, we have DC cables, DC power cables, but also you can connect it to the AC grid. So there are different options also here. Okay, I think there are no more questions for the moment. So I think we are done. And there was an inquiry to share the presentation. We will share the presentation and, of course, the recording. So please feel free to look at that. And if you have any further questions, please do not hesitate to contact us at any time.
Yeah, we're looking forward to your questions.
Thank you.
Thank you very much, everyone. And thank you for joining today.
Right.
Bye.
Thank you. Bye-bye.